Hey guys, welcome to the Unbounded Medium. Today's topic is going to be dynamic rate switching. Within the industry, there are going to be a number of names that are used interchangeably for dynamic rate switching. Some people simply abbreviate it as DRS, whereas others will use dynamic rate shifting instead of switching. You also see dynamic rate selection, adaptive rate selection, and automatic rate selection. For our purposes, we're going to stick with dynamic rate switching. Each 802.11 has a range of available data rates. And those multiple data rates, they're going to provide 802.11 stations with the ability to communicate at the highest possible data rate dependent upon current RF conditions. Those data rate transmissions between the AP and client, they'll shift down or up depending upon signal quality between those two radios. Signal quality is typically represented with a combination of RSSI, received signal strength indicator, and SNR, signal to noise ratio. The quality is based on current RF conditions, but it also has a correlation to the distance between the AP and that client, which I'll demonstrate later in another slide. This does bring into the topic of modulation and coding schemes. This isn't intended to be a deep dive into that topic, but essentially understand that less complex modulation and coding schemes can be successfully decoded or interpreted by a receiver in kind of less than ideal RF environments and or increased distances away from the AP and still achieve BSS connectivity, basic service set connectivity, even at lower data rates. Of course, the reverse of that is true. So as data rates increase, resulting in more complex modulation and coding schemes, the signal quality also has to increase in order for that client to successfully interpret that data. Now, as you can see at the bottom of our slide here, within a given BSS, they're going to be kind of basic or required data rates. So in order for a client to successfully connect to a BSS, it's going to have to support that basic or mandatory data rate. But there's also kind of a grouping of data rates, sometimes called supported or optional, that stations in a BSS can use when communicating within that service area. A typical use case that you'll see in a lot of designs today, you'll see folks, even myself, will disable data rates of 1, 2, 5.5, and 11 megabits per second and set, for example, a mandatory data rate of 24 megabits per second. Essentially, that's eliminating the ability of 802.11b devices to connect to your network. And then on top of that, you would see, for example, data rates of 24, 36, 48, and 54 megabits per second set as that supported or optional data rate. Now, we're saying data rates. One quick topic on data rates is, data rates versus actual throughput of what the client sees are typically drastically different. And the reason for that difference is medium contention. Wireless is a half duplex medium, and so stations are constantly contending for their opportunity to talk on the medium. Only one guy, one station per channel is able to talk at any given time, so they're constantly vying for the opportunity to talk. That chatter, that mechanism is what's taking a large chunk of the available bandwidth off, typically 40 to 60%. So if we use a real scenario, let's say we had a classroom of 30 iPads. Let's call it the iPad Air 2, which is a 2x2, 2 spatial stream 802.11 AC tablet. And let's say we're using 20 megahertz channel widths. In that case, it has the capability of doing 173 megabits per second of a data rate. But in our scenario, we got 40% of the available bandwidth being taken away by that medium contention, which leaves us 69 megabits per second to hand out to the client. But if you recall, in our case, we've got 30 iPads in this classroom. So I got to take that 69 megabits per second and I've got to distribute that across those 30 iPads. So in actuality, each iPad is only getting 2.31 megabits per second of actual throughput. So obviously, drastic difference between 173 megabits per second data rate versus the actual throughput of 2.31 megabits per second. So with all that said, the objective of dynamic rate switching is to facilitate the upshifting and the downshifting of data rate optimization and improve performance based on signal quality that is being received or sent by stations in a BSS. So let's look at how this works in Wi-Fi networks. This obviously is for illustration purposes only. We know that there's no such thing as concentric perfect circles with signal propagation in today's wireless networks. But let's say that we have an AP in the middle of this service area, and that we also have a client in this service area. And when that client first associates, it's going to connect at a determined data rate based on certain algorithms. Now, those algorithms are determined by radio card manufacturers, and each manufacturer is going to have their own kind of secret sauce of how they determine what that rate's going to be. For example, some manufacturers will base that decision on RSSI thresholds, as well as packet error rates and retransmissions, whereas others may look at strictly the combination of RSSI and SNR. But this is because the 802.11 standard does not specify requirements around dynamic rate switching. And so manufacturers kind of implement their own variation of how they want to determine what rate the client device is connecting with. And so you'll find that you can have two clients of different manufacturers within the same physical area connected to the same AP associated at different data rates. But for our purposes, let's say this client associated at 12 megabits per second. Now, wireless is a mobile technology, and so most of our clients are going to be moving throughout our service area. So in this example, this client has decided to move closer to the AP. In this case, typically the closer you get to the AP, the higher your RSSI is going to be, as well as your SNR. Typically, you also have lowered your packet loss and you have lower or lesser retransmissions, all of which are contributing to a higher signal quality. And in this case, the client has now improved its data rate to 36 megabits per second. But once again, we're mobile, so that client has decided that it needs to move again. And this time the client has moved to the edge of this AP service area. Now the client, as you can see, the client's data rate has reduced to 6 megabits per second. But you can kind of see the concept that as clients move closer to the AP, the signal quality typically improves, and as it moves further away from the AP, the signal quality typically decreases. Obviously, the data rate will adjust accordingly, but be careful with assuming that signal quality is always tied to distance away from the AP. For example, in our scenario, let's say the client has decided to move closer to the AP, but in this case, when he moved closer to the AP, he actually moved to an office that was, in an area where it had 3 interior walls in between itself and the AP. So if we were to demonstrate that, in this case, there's those 3 interior walls in the office where that client moved to, causing attenuation, as well as there may be other RF conditions in that office also contributing to lower data rates. But in this case, the client actually connected at 6 megabits per second instead of the 24 megabits per second that the illustration would allude you to. There's one more concept I hope you kind of visualized with the illustration. Data rate coverage areas get larger the further away the client gets from the AP, because of lower order modulation and coding schemes are typically easier to code or interpret. So basically, this is meaning that lower data rates have larger coverage areas than higher data rates. So guys, that wraps up our topic today. That's dynamic rate switching. I trust the video was informative, and I appreciate you watching.